Welcome to the topic of waves. In this section, we will explore how waves transfer energy, the different types of waves, and how we can describe and measure wave behavior. Course and specification overview of waves. The specification of waves is divided into two broad areas: progressive and stationary waves, and refraction, diffraction, and interference. Students are expected to understand waves as a means of energy transfer without net transfer of matter, and to apply this idea across mechanical waves, such as sound and waves on strings, and electromagnetic waves, such as visible light and microwaves. Core physical quantities are defined precisely, including displacement, amplitude, wavelength, frequency, period, phase, and wave speed, with clear expectations that students can use and rearrange equations such as V equals F and F equals 1t. Progressive waves and energy transfer, wave equation, period, and phase. A progressive wave is defined as a wave that transfers energy from one point to another without any net transfer of the medium itself. This distinction is fundamental, as it explains why water waves move energy across a lake while individual water particles merely oscillate about fixed equilibrium positions. In mechanical waves, such as sound or waves on a string, particles vibrate due to restoring forces, whereas in electromagnetic waves the oscillations occur in electric and magnetic fields. Several key quantities describe progressive waves. Displacement is the distance of a particle from its equilibrium position at a given moment and can be positive or negative. Amplitude is the maximum magnitude of displacement and is directly related to the energy carried by the wave. Larger amplitudes correspond to greater energy transfer. Wavelength is the distance between successive points that are in phase, such as crest to crest, and is measured in meters. Frequency is the number of complete oscillations passing a point per second, measured in hertz, while the period is the time taken for one complete oscillation. The wave equation V equals F links wave speed, frequency, and wavelength, showing that for a given medium the speed of a wave is constant, so frequency and wavelength are inversely proportional. For EM waves, the wave speed in a vacuum is c equals 3.0 times 10 ms to the power of 1, a value that must be recalled accurately for examinations. The period t is linked to frequency by F equals 1t, reinforcing the idea that frequency describes how rapidly oscillations occur. Phase describes the position of a point within a wave cycle, measured in radians, degrees, or fractions of a cycle. Two points are in phase if they have the same displacement and velocity at the same time, and their phase difference is a multiple of 2 pi radians. Points in antiphase differ by pi radians and have opposite displacements. Transverse waves and polarization, longitudinal waves, and sound. Transverse waves are characterized by oscillations that occur perpendicular to the direction of energy transfer. All electromagnetic waves as transverse, and this transverse nature allows them to be polarized. Examples of transverse waves include waves on a string, water surface waves, and all forms of electromagnetic radiation from radio waves to gamma rays. In these waves, crests and troughs are visible indicators of displacement. A polarized wave oscillates in only one plane, which can be achieved by passing light through a Polaroid filter. Longitudinal waves differ from transverse waves in that the oscillations of particles occur parallel to the direction of energy transfer. Sound waves propagate through media such as air, liquids, and solids via a series of compressions and rarefactions, where particles oscillate back and forth about their equilibrium positions. Unlike electromagnetic waves, longitudinal waves cannot travel through a vacuum, a fact that provides strong evidence for their dependence on a material medium. For example, loudness is related to amplitude, while pitch is related to frequency. Principle of superposition, formation, and properties of stationary waves. The principle of superposition states that when two or more waves meet at a point, the resultant displacement is the vector sum of the individual displacements. This principle applies to all types of waves. Constructive interference occurs when waves meet in phase, producing a resultant wave with greater amplitude, while destructive interference occurs when waves meet in antiphase, reducing or cancelling the displacement. Importantly, superposition does not violate energy conservation. Energy is redistributed rather than destroyed. Stationary waves, also known as standing waves, are formed when two waves of the same frequency and amplitude travel in opposite directions and superpose. In a stationary wave, nodes are points of zero displacement where destructive interference always occurs, while antinodes are points of maximum displacement due to constructive interference. Unlike progressive waves, stationary waves do not transfer energy along the medium. Instead, energy oscillates locally between kinetic and potential forms. Stationary waves can be formed on strings, in air columns, and using microwaves. On a stretched string fixed at both ends, the ends must be nodes, leading to specific allowed wavelengths and frequencies. Interference and Young's double-slit experiment, diffraction and refraction of waves. Interference occurs when two coherent waves overlap and superpose, producing a pattern of constructive and destructive interference. Coherence requires a constant phase difference and the same frequency, conditions met in Young's double-slit experiment by using a single monochromatic source. Constructive interference occurs when the path difference is an integer multiple of the wavelength, while destructive interference occurs at half-integer multiples. Diffraction is the spreading of waves when they pass through a gap or around an obstacle, and it is most significant when the gap size is comparable to the wavelength. For example, longer wavelengths diffract more, which explains why sound can be heard around corners more easily than light can be seen. Diffraction gratings are a key application, producing sharp interference patterns that allow precise measurement of wavelength. Refraction, in contrast, occurs when a wave changes speed as it passes from one medium to another. This change in speed leads to a change in wavelength while frequency remains constant. The Doppler effect is the change in observed frequency caused by relative motion between a source and an observer. For example, a moving ambulance siren sounds higher in pitch as it approaches. In practical experiments, we can measure wave properties using equipment such as ripple tanks, signal generators, and oscilloscopes. Accurate measurements allow us to calculate wave speed and analyze wave behavior. In this topic, we have explored wave properties, equations, and behaviors including reflection, refraction, interference, diffraction, and the Doppler effect. Understanding waves helps explain many physical phenomena around us. Thank you for watching.